Good afternoon, everyone. Welcome to session CMP203, Driving Innovation and Results with High-Performance Computing on AWS. I am Srinivas Tadepalli, and I lead our worldwide go-to-market teams for advanced computing, which is basically high-performance computing, accelerated computing, and quantum computing workloads. I have the distinct pleasure of being joined by two of our customers today, Harsha Gurukar from Merck, as well as Jake Mully from PhysicsX. So they'll be joining me later in the presentation, talking about their journeys on AWS. So without any further ado, let's get started. So this is the outline for our talk today for the next 45 minutes or so. Now, I'll be kicking off with what are some of the common HPC workloads that our customers across a variety of industries are running on AWS. We'll then take a deep dive at what are the key HPC services that these customers are using. Harsha will then talk about Merck's journey on AWS, followed by Jake talking about PhysicsX's journey on AWS. And then I'll come back and talk about some of the interesting aspects that we are seeing from our vantage point in terms of convergence of the high-performance computing and AI workloads. And then we'll finish it off with some closing remarks. So let's get started. High-performance computing is all around us, whether it is the car that you drive or the airplanes that you fly within the product design space. Customers across these industries use high-performance computing applications such as finite element analysis or computational fluid dynamics in order to design the right product. Within the healthcare life sciences, which you'll hear from Harsha later today, we have customers like Merck and many others using AWS for their mission-critical modeling and simulation workloads. Weather and climate is another key area that customers have been using AWS for a long time. Semiconductor design, whether it is your front-end EDA design or back-end EDA workloads in terms of designing the chips and bringing them faster to market. Energy. Within the energy space, we have many customers using workloads such as seismic processing and reservoir simulation in order to find the oil and natural gas deposits below the Earth's subsurface. Within the financial risk simulation space, we have customers across insurance, banking, quant trading, et cetera, using AWS. Academic research is another important area where customers have been using HPC for a long time. And finally, generative AI and large language models. The way we look at this is it's another HPC workload that kind of uses the exact same infrastructure in terms of compute, storage, and networking in order to train these large foundation models. And this is a very, very tiny subset in terms of some of our customers across these different industries using AWS every single day for their production workloads over the past many years across all these different industries. One of the interesting aspects about these advanced computing simulation workloads is they come with different compute and throughput characteristics. For example, if you take a look at these automotive and aerospace product design and engineering simulations, we call these as tightly coupled workloads. What that basically means is you take a single HPC job, and then you actually scale up on multiple compute nodes or multiple GPU nodes in order to reduce the runtime. Similarly, within other areas such as genomics or within financial services running Monte Carlo simulations, we call these as loosely coupled workloads. You're running thousands or tens of thousands or even sometimes hundreds of thousands of them in an embarrassingly parallel fashion. More recently, we are starting to see the emergence of accelerated computing over the last decade or so, where our customers are using purpose-built accelerators or even GPUs to speed up their workloads. And then also visualization, whether it is VDI or whether it is for large-scale rendering across compute farms for visual computing and spatial computing. These are all visualization workloads. All these different workloads have different characteristics, thereby dictating different compute, storage, networking, and orchestration needs. So let's take a look at what does this look like if you were to run these on AWS. At the end of the day, you basically have a stack of services, right? Starting with compute and networking. On top of that, you have a storage. And then you need some sort of an orchestration tool in order to bring this compute, storage, and networking together. And then finally, you're running these end-user applications. So let's dive one level below. On the compute and networking side, our customers are using CPU nodes, GPU nodes, FPGA nodes, custom ASICs, et cetera. And then EFA is our elastic fabric adapter for our low latency network. We'll talk about that in a second. And then on top of that, you have a variety of storage services, be it either EFS, EBS, S3, FSXL, so on and so forth. And then when it comes to the orchestration, customers have choice to use Slurm, EKS, or any other orchestration of your choice. And then on top of that, you're running different class of workloads, whether it is LLM training, whether it is modeling and simulation, whether it is weather and climate, so on and so forth. If we were to get even more specific, this is how the stack looks like for a specific application. You can have the choice of using a specific CPU type, such as HPC 7A, and we'll talk about that in a second, or a P5 instance offering NVIDIA H100 GPUs. When it comes to storage, our recommended service is FSX for Lustre, and we'll again deep dive in a second. And then when it comes to orchestration, we can use services like Parallel Computing Service or Parallel Cluster or any of our partner solutions. And then, of course, finally, you have the end user applications, whether it is NAMD for running molecular dynamics types of simulations, Fluent or Star CCM Plus, et cetera. These are some of the applications from our ISV partners running modeling and simulation workloads. This is really what it comes down to, right? And compute, storage, networking, orchestration, and applications. So if I take a step back, and you can see here, AWS has been investing within the HPC and the advanced computing space for almost a decade now, starting all the way from AWS Batch with nice DCV, Annapurna Labs coming on board with our Nitro, so on. And then fast forward, you can see we have several dozens of services purpose-built for our customers to be able to run their mission-critical HPC workloads. The ones in orange is our custom silicon innovation around our Graviton, our Trainium, as well as our Inferentia for general-purpose compute, large-scale training, and inference. As I said, when it comes to high-performance computing on AWS, it boils down to 5 pillars: compute, storage, networking, orchestration, and visualization. All of these services delivered through a secure HPC infrastructure. Before we dive deep into each of these services, let me take a moment to talk about security. Security is our top priority at AWS. We provide the most secure infrastructure for our customers to run their production and mission-critical workloads. And that is done through security automation that in turn drives speed and agility, providing end-to-end security and guidance. And this is just a very high-level snapshot of our key services around security, identity and access management, or IAM, detection and response, network and application protection, data protection, and finally, compliance. And all these details are available on our websites. Let's now dig into our compute aspect. AWS currently offers more than 750 EC2 instance types. EC2 stands for Elastic Cloud Compute. What we have done is, within the high-performance computing space, we have purpose-built a set of SKUs that delivers the best price performance to run all of your HPC workloads. So what you're seeing here on the screen is our purpose-built SKUs specifically for our CPU nodes. For example, our HPC 7A instance, it's actually our 7th generation instance based on the AMD platform, specifically the AMD Genoa, providing 192 physical cores, 768 gigabytes of system memory, and 300 gigabit EFA. The interesting aspect about all these HPC instances or HPC nodes on AWS is hyper-threading is turned off by default because that's what customers care about. And we have these available in deep pools, and all of these instances offer a low latency network EFA. Similarly, HPC 7G is our Graviton ARM-based instance, purpose-built to run a class of workloads such as computational fluid dynamics, computational chemistry, molecular dynamics, weather and climate workloads. We also have our data and memory-intensive SKU. It's called the 6ID. It's based on the Intel Ice Lake platform. And you can see here within the HPC space, we call this as a fat node because it's got different set of characteristics. Less cores, lots of system memory, and lots of local disk to be able to run your data and memory-intensive applications. And finally, we also have our highly optimized high-frequency nodes, specifically geared towards our customers within the semiconductor space running your chip design and EDA workloads. Last year at re:Invent, we pre-announced our Graviton 4 instance that was made generally available a couple of months ago. Graviton 4 is our newest generation of EC2 instances available across CMR families. Our largest node has 96 cores, ARM Neoverse v2, 2 MB of L2 cache per core, 12 channels of DDR5 with 96 PCIe Gen 5 lanes, providing almost half a terabyte per second of memory bandwidth. And this is for single socket. So our dual socket nodes have a terabyte of memory bandwidth, ideally suited for running a variety of HPC applications. So let's take a look at how our Graviton 4 performs to our prior generation of our Graviton instance based on Graviton 3 or HPC 7G instance. For example, if you take our Graviton 3, which is our HPC 7G, and we have normalized our performance across a variety of applications. So you can see here, the first two sets of applications are for WRF, which is a very commonly used weather research forecasting model within the weather and climate industry. These two applications provide at least an average of 23 to 25% improvement generation over generation. The next one is OpenFOAM. You can see here again, across OpenFOAM, across ANSYS Fluent, two specific applications, the performance uplift is anywhere between 19 to 27% generation over generation. And even within the computational chemistry space, running applications such as GROMACS, you're seeing a decent 5 to 10% improvement in price performance. So going from one generation to the other generation, you're seeing a pretty interesting uplift on a per core basis when you're running these applications. So that's on the CPU side. Now let's take a look at our GPU nodes for our HPC and VDI workloads. Again, AWS has been partnering with NVIDIA for more than 13 years, offering the latest and the greatest GPU instances for our customers. What you're seeing here is our latest offering in terms of our P5e instance based on the NVIDIA H200 or the Hopper 200 platform. Our P5 instance is a generation prior, which is our H100 instance. Similarly, we also have our G family of instances. G6e is based on the L40S, and G6 is based on the L4. And just yesterday, hot off the press, we also announced our P5EN instance. It's a refresh of our P5e instance, offering 3,200 gigabits per second of network throughput, and also have the exact same set of nodes, 8 H200 nodes. But we also have our EFA v3, providing really low latency, high bandwidth, and high throughput for these HPC and AI workloads. So that's on the compute side. While compute is super important, especially for running large-scale API workloads, we also need a high-performant, high-throughput, high-bandwidth, low-latency network. On AWS, our networking protocol is EFA, stands for Elastic Fabric Adapter. It provides the OS bypass, providing the GPU direct RDMA capabilities for our customers, so you can bypass the CPU so that these applications can tap into the memory of the other nodes or CPU nodes or GPU nodes. Now, what you're seeing on the extreme right is actually the performance, a linear scalability of a CFD application called StarCCM+. So we have taken a 1.4 billion cell model. It's a pretty large model in terms of the size. And you can scale that up to 400 nodes. And you almost see a near linear scaling. So we're talking about running a single application or a single job on almost 40,000 cores or 400 nodes, providing near linear scaling. So that's on the networking side. Now let's take a look at our storage options. Again, as I said earlier, we have a variety of storage options, starting from S3, EFS, EBS, and various versions of that. HPC customers always require a high-performance file system. So we do have services like FSX for Lustre and FSX for NetApp on tap, purpose-built for HPC applications, both of them providing sub-millisecond latency. If you have workloads that actually requires a POSIX dependency, our recommended option is FSX for Lustre. If you have applications that require support for both NFS and SMB, our recommendation is to use NetApp on tap. Both have interesting characteristics, purpose-built for offering a variety of HPC applications. Moving along on the orchestration stack, we have 4 different services to serve all of our customer needs. The first one that our customers have been using for the longest is AWS Batch. It's a cloud-native scheduler that is fully managed and is integrated with the rest of the AWS services that provides massive scalability, and it is ideally optimized for resource provisioning, offering the best price performance, especially for running large-scale scale-out applications. An interesting story about AWS Batch is one of our recent customers called Institut Pasteur, based out of France. They were able to spin up 2 million Graviton cores and able to index the planet for all the viruses that are out there. And by the way, this actually won the Best Cloud HPC Use Case award at the recent supercomputing conference 2 weeks ago. And this customer was using AWS Batch to be able to scale across 2 million Graviton cores, multiple regions. Our other service, especially for running tightly coupled applications, is AWS Parallel Cluster. AWS Parallel Cluster is an open source tool managed and maintained by AWS. Our customers have been using this service for a very long time as well. Parallel Cluster brings all these different services together, which is compute, storage, networking, and visualization. While Parallel Cluster is a great service that many customers have been using for a long time, our customers have been requesting us to offer a fully managed service with all the goodness of the Parallel Cluster capabilities. In order to address these needs, we launched our Parallel Computing service a couple of months ago. This is a fully managed cloud orchestration, giving you the ability to access resources at scale on AWS. It provides job management capabilities using Slurm, with more schedulers to be added in the near future. It also helps our customers easily migrate without writing any code or script changes. The interesting aspect about parallel computing services, it provides a unified compute and remote visualization capability, allowing our customers to dynamically scale and up and down in terms of resource provisioning, ability to bring your own applications, and finally, we provide in-depth telemetry for all of your cluster as well as jobs. The other important aspect about parallel computing services, it really addresses the needs of the different personas within the HPC industry. Whether you're a system administrator, whether you're the end user, such as a scientist or an engineering running applications on these clusters, or whether you're a developer or an ISV partner wanting to develop applications on top of AWS, PCS is the tool for you all. And finally, Research and Engineering Studio. This is a portal that provides our customers the ability to easily manage and deploy projects, including cost and budget allocation and management. As the name suggests, it is a portal, and this is how the UI looks like. You can see customers can easily create projects and assign users to these projects and assign permissions, so on and so forth. And with this, you can actually connect this to the parallel computing service, so you can use Research and Engineering Studio as a front portal and parallel computing service as the orchestration tool to stand up and stand down your HPC clusters. Research and Engineering Studio is also used by our customers for managing their virtual desktops environments in conjunction with the HPC applications. Now, in order to see all of these different services in action, let me introduce Harsha Gurkar from Merck, and he's going to talk about how Merck has been using AWS in order to run their production workloads at scale.
Thanks, Srini. Good afternoon. I'm going to switch gears, not talk about bits and bytes, but I'll talk about our journey from on-prem to AWS. This sort of resonates with a lot of people I talk to because we've had HPC team at Merck since the early 1990s. And so we got very mature workloads on-prem, and moving that anywhere is a tough proposition. So let me start with a quick, this is not my presentation. Okay, my fault. So let me start with an introduction of how complex the drug discovery journey is. It generally starts with discovery, moves on to preclinical, then moves on to early development, and then several phases of clinical trials. So each one of these stages are pretty complex. For example, with discovery, you first figure out which disease you want to target and find a biomarker, which is generally a protein in that disease, and then figure out a mechanism to dock with that particular protein in the hopes of either changing the structure of that protein itself or delivering a compound to cure the disease. So it takes about 8 to 10 years and $1 billion or $2 billion to bring a drug to market. So it's a very expensive and time-consuming process. Any place we can cut down on costs or the time to market is a really huge, and it's a good thing, obviously a good thing. It's not just the finance part of it, it's also, we at Merck believe it is delivering drugs to patients that require it. The earlier, the better. So how can we do this? Our R&D has to be very innovative, and we need to enable our R&D with the right tools. HPC is one of those right tools that gives them the ability to innovate, and that's where HPC comes in. And at Merck, like I said, we have had 3 decades of experience with HPC, but now it is time to modernize, start inventing better, and move on to the next stage, hit it out of the ballpark. Cloud is the answer. Now, the value case itself, what can AWS offer us? With the on-demand services we get with AWS, this long drawn process of budget forecasting and procurement and then setup is going to be history, right? We don't need any of that. The budgeting is still there. It's not capital anymore. It's going to be expense. So, and the sysadmin, the administration is still there. It's not the hardware in the data center. It's infrastructure as code. And it's the productivity itself will increase because we will enable our research scientists to think less about IT and more about research outcomes. So for us to do that, we need to automate. We need to give them services that will really help them do the research rather than trying to move data from one place to the other, trying to figure out which CPU to use, which cluster to use, wait in line on a shared infrastructure to get their jobs through, and so on. So the AWS services really offer a bunch of services which we can enable and make them be more productive. So success criteria, how do we know what good is? The first thing we wanted to do was user adoption. We have existing users, and there is a whole bunch of other users, including bench chemists, biologists, that don't use HPC because they don't have that HPC skill set, or definitely don't have the cloud skill set either. So key to adoption is user interface. So they just go to a website, it's all web interface, use a GUI, pick a few things, and then wait for the results. And all along the way, obviously, we're going to monitor it and give them information of where their job is and how it is going. And the other thing is metrics. How do we measure that we're successful? The number of platforms we migrated, the number of users we migrated, the number of cores and storage we decommissioned on-prem is all part of it. Then there is also FinOps. We don't have a chargeback model, but we need to forecast the spend. And to do that, what we are doing is we're exposing total cost of ownership, cloud consumption cost per job, per user, that kind of metrics to our user community. Now, how do we fund this? We have this on-prem infrastructure, and we said we have a value case, we need to go to the cloud. How do we fund this? There was we had an enterprise-sponsored, board of directors-sponsored Modernize IT program. And like everybody else, we got a consultant company to come and do a check on our landscape. And when they got to HPC, they said, let's keep it aside and call them Big Rock, because they use a lot of infrastructure. We really don't know what they do. So we were termed a Big Rock. So what we did next was we double-clicked on our Big Rock, analyzed it further, and said there is both a financial value and a business value. The financial value was to mitigate a large tech debt we had accumulated over the years. And the reduction of data center and potentially sysadmin costs. And the business value is we figured out there was 40 million and odd wait hours, millions of wait hours on our systems annually. So anything we can do to reduce that, in theory, on AWS, we can bring that down to zero, right? Let's not go there yet, but anything we can do to reduce that is a great business value. And if we do everything we said we'd do and give researchers the ability to innovate, there is potential for early revenue realization. As soon as you say that, people pay attention to it. So we can bring drugs to the market faster, you get your revenue faster, kind of thing. And the business case went through several rounds of approval and all that, and we got it approved. But in the process, we were asked some questions. So show us the proof of value. So we picked a workflow, and generally takes about 90 days to complete on-prem. And we showed that we could get the outcome in less than 30 hours. And that was a really good use case and proof of concept, proof of value that this business case has real value. So what we also did was our team, a couple of my rock stars are here today, our team did not have the bandwidth to do this ourselves. If we did this, it would take us 6 to 8 years. What good is that? So we engaged AWS professional services to do the heavy lifting on our behalf. Our team still led everything. We engaged them to do the heavy lifting. Here are some of our success stories that to the last 18 months. We're at this for the last 18 months or so. Here are some success stories. One of the first things we did was we enabled, to enable user adoption, we customized Open On Demand. Open On Demand is an open source tool that gives a single point of access to your HPC resources. What that gave us was file transfers, drag and drop kind of the file transfers, but up to a certain limit. But if there was large data transfers, it still was admin assisted. Then we created an interactive desktop for visualization, and we used NiceDCV. And we had NiceDCV CPU ones, and we had NiceDCV GPU ones, so people could use either or, depending on what they need. And we gave access to the clusters. We had legacy job schedulers in Grid Engine and PBS Pro. We enabled those, and we gave access to those command line access. And then there was a GUI that is part of Open On Demand that will let people who are not very comfortable with HPC or cloud to create, submit, monitor their jobs. So this actually enabled user adoption. The CLI was required for our power users, because as soon as you said GUI to power users, they were like, well, why are we even talking about this? But then they came back to us and said, well, there is this one custom workflow that everybody uses a lot. We could use this custom GUI for that. So we enabled that kind of stuff. And the new users, definitely, who are not command line savvy, the graphical user interface definitely helped. Then we made a conscious decision to do a lift and shift. Like I said earlier, we've been at this for over 30 years, so there is a lot of legacy workflows. And some of them have been inherited from a researcher to a researcher. And they know how to use it. It's all command line based. And that is one part. The other part is researchers have deadlines like we do also. So they really don't have the time to learn something new, validate it, and all of that. So doing this lift and shift, and we entice them by saying, this is not just lift and shift, we'll also give you auto scaling. So you can scale this while we do the lift and shift. So what we did was we replicated our on-premise environment, same storage paths, same modules and tools. And so the bottom line was a researcher who was a command line researcher, instead of logging into an on-prem head node, they just logged into an AWS head node. And everything should work. Well, there's little tweaks maybe here and there. So that was really became a low-hanging fruit for us to start migrating, because we need to show results. Somebody gave us money, right? We need to show results. So that was good. And again, the cloud solution brought in a lot of value. Like I said, we could use existing workflows, minimal testing, cloud elasticity in short order. They didn't have to go through a whole POC and all that to figure this out. And then there was a side benefit of reduction of on-premise tech debt. Data lifecycle management. On-premise was a really tough proposition. It's like researchers just store data, don't delete it. Anybody who has dealt with researchers know that. And we have tons of backup on tapes, because we're 30-year legacy, right? And it was really hard. We tried several things. The purging and the data retention policies were ineffective. We looked at a few third-party vendors that didn't suit for our environment. So it was very ineffective. So we had this 40, 50 petabytes of data sitting all over the place. It was all ad hoc, so it was all over the place. It was impossible to manage the data lifecycle. And basically, services, storage services in AWS gave us a nice way to do this, an easy way to do this. So we went to the researchers and said, if you haven't created this in the last 3 years and have not used this for a year, we'll archive it. We'll archive it, and we will automatically archive it, no involvement from them. And then if you need to look at it, here is a EC2 instance you can log into. What we did in the background was used AWS Gateway to expose their data, and they mostly wanted warm and fuzzy that it's there. Right? Researchers never want to get rid of data. So that was a quick win. What we did not do was set retention policies. So we put everything on S3 INT that gets tiered automatically. We can also set retention policies. We did not because there were a lot of questions. There was confusion on somebody saying, I want a 5-year retention, somebody saying, I want 10, I want somebody 35. I even heard 100-year retention. So I said, we'll deal with this at another time because AWS Services offers you to be able to set that at any time. So that was a easy decision. So data lifecycle management, going forward, everything goes directly to the cloud, and we'll apply retention policies and at least tiering policies upfront. Data science notebooks. This was another heavily used platform. And it was on-prem. We stored it with RStudio, and then we had a separate Shiny app and all of that. And what we did was we also set up a POSIT workbench on-prem. And it was sitting on hardware that was going out of warranty. And so what we did was we set it up on the cloud and started moving user by user. And the added benefit there was we integrated with GitHub, and we also integrated with HPC clusters. So they could scale. If they had a large data set, they could scale to HPC from within the notebooks. AlphaFold, again, groundbreaking AI/ML application for protein structure prediction. So AWS has Healthomics, and AlphaFold is a ready-to-run service. So what we did was we added a web interface to it. It was just basically a Shiny app for users to go to this Shiny app and just pick a few things, and out came a result after a few hours. Obviously, they got notification when it did, and it gave 5 different predictions. And this is what they would say. They click on a link that they got saying your job is complete, and this is what they say. Again, that Shiny app made the non-HPC savvy or non-cloud savvy folks to use AlphaFold, and it's used widely. And the last use case is CryoEM. CryoEM, again, generates a ton of data, 16 terabytes a day, and so now we're adding more CryoEM, so it could be 32 terabytes a day or so. So the data management challenge is huge. How do you back it up? How do you move it? How do you compute on it? The whole thing. So what we did was we figured out a way to directly transfer the data from the CryoEM's, the instruments cache, right, onboard cache, directly to AWS and compute on there. And since we back it up with S3 INT, data management is automatic, and it doesn't burden the researcher to do it. And again, doing all this in short order had the side benefit of reduction of on-premise infrastructure. We use the same architecture to data that we acquire from external vendors, cryo data that they just put it in our bucket and we take it from there. And this is what it looks like. This is an example of a compound solved by cryo-EM. Again, don't ask me for specifics of it, what exactly it is. Looks cool. All right, thanks, everyone. And here is Jake from PhysicsX for his talk. Thanks, Jake. This green one takes you forward. Top.
Thanks, Srinivas and Harsha, for the warm introductions. For a quick intro to me, I'm Jake Mully. I lead PhysicsX's cloud engineering efforts. Through the next 10 or so minutes, I'll give an introduction into what PhysicsX is, what we do, and how we do it using AWS. First, an introduction into PhysicsX. Oh, no, this is my title slide. So PhysicsX are building AI to accelerate innovation, improving the design, manufacturing, and operation of complex physical products and machines. We work at the intersection of computer-aided engineering, simulation, so CAE, AI deep learning, generative design and control. Our purpose as an organization is to be able to build beyond human imagination to meet the most important challenges of our time. And we do this across advanced industries, such as renewables, materials, semiconductors, automotive, aerospace, and more. From our work, we have a clear hypothesis. We can change the way conventional engineering is done by reducing iteration time on product design and development from hours and days to seconds, by moving from simulation to inference and reducing the cost of running simulation too. We know product design is typically bottlenecked by CA-dependent processes, which require time and effort to get right and explore every combination of physical design. So we've been building large physics models, LPMs, which learn to replicate the behavior of physical processes and have shorter run times with substantially less compute per iteration. As an organization, we're relatively young. We're about 5 years old, but we're 100+ people in multidisciplinary teams across software, data science, machine learning, simulation, and AI research. If we have a look at conventional CAE and conventional meta models, conventional CAE numerically solves differential equations arising across conventional engineering and mathematical modeling. But we know there are typical pain points for this. There are long setup times and intense data processing to get into a good shape to run CAE simulations, which then require long computational time across hours and days and further restrict design exploration. If you're designing a physical product, such as a jet engine, your feedback loop takes days to get the output, and then you iterate, and you keep running in this cycle to get the optimum output needed. This often requires expert knowledge across the domain you're working in. And if you look at conventional meta models too, you can expedite computation using reduced order models using reduced order models and response services of simulations, but these have their own pain points too. It's much less accurate than numerical simulation or deep learning. It has difficulty capturing nonlinear behavior or complex dynamics, and often requires sacrificing physics-informed constraints. So this is a large physics model. They learn to replicate behavior of one or more physical processes. For example, if you're designing an aircraft, LPMs can learn the relationship between the design of the wing on an aircraft and both the pressure field over its surface and the structural stresses within. Compared to conventional CAE alone, or conventional meta models, these models have shorter runtimes, allowing for faster iterations, changing from days and hours to minutes and seconds across substantially less compute. Further, you can automate this process, as we'll see in the next slide. And by doing this, it allows for exploring increased designs, leading to a more optimized design across real-time process optimization. This can also increase manufacturing throughput for the people we work with, and over time, the models improve and learn, which we've dubbed active learning, and it can capture institutional knowledge and explore physical product design across known constraints. It's already had applications across products used day to day through the customers we work with. And large physics models isn't just one model. There are many models people can use, and our learning and experience suggests that there is not a single model that fits all use cases. By using large physics models, you can build, deploy, change, experiment really quickly, and become more and more agile as you design physical products, rather than rebuilding data pipelines from scratch using conventional CAE processes. If we have a look at this diagram, this shows a typical design cycle for a product, augmented on the right-hand side with active learning and large physics models. On the left, you create a baseline using a geometry, run a CAE simulation, optimize it, and then create a geometry, run a CAE simulation, optimize it. And once you're happy, you can use that to train a model. And through the active learning loop, it will optimize, simulate, and train itself continuously to create an optimized design more quickly. We've used this same flow internally and with our customers to augment teams and prior workflows to improve design. People typically associate time to market for products with the number of CAE runs and how long they take. And we think with active learning loops, we can reduce product development time. Even if you're using the same CAE runs from a conventional method, because it is automated, it will retrain itself over the weekend, at midnight, whilst you're at reInvent. And the dimensions and outputs explore more space compared to conventional methods too. If we take a look at a real-world example, this is some work we did with a medtech startup developing a novel type of artificial heart. It's called an LVAD, a left ventricular assist device. Typically, if you require a heart pump, they're quite large. You tend to have a tube coming out of your chest, which can lead to complications through infections. So the objective of this medtech startup is to reduce complications related to blood damage, for example, bleeding or clotting, which result from the application of mechanical pumping action. And this slide shows, if the video starts, but it might not. Okay, if I go back, maybe it will start. Okay, yes. So you can see the iteration through an active learning loop where it's retraining itself. And this is real time. This isn't sped up or slowed down. So in the time I take to talk, you can see it's going through iterations. We're nearly at 20 to calculate the correct pressure for the LVAD. Ultimately, this product is currently this heart impeller is currently in the product you saw in the previous slide. It's going through pig trials in hopes that one day this can be implanted in humans. With this particular device, it's much smaller than traditional heart pumps, so you can actually get rid of the wire that comes out of your chest too, further reducing complications. And ultimately, the reason we're here, it was built on AWS. So we'll have a look at our architectures. Over the past few years, we've been augmenting our on-premise setup, where we have hundreds of cores, many GPUs, by using AWS services that Srinivas was talking about earlier. We typically have two types of workflows, machine learning and high-performance compute for CAE simulation. And we're currently building an enterprise SaaS platform for ourselves internally and our customers to use day to day, providing them with access to our large physics models and to allow them to self-serve their own requirements. So if we look at our high-performance compute architecture, we can see that we're using parallel cluster with SLAM. One of the lovely things about parallel cluster is everything is already set up for you, and the SLAM component is what our researchers and our teams are used to using anyway, so there's no learning curve for them to use these tools. We scale through hundreds of HPC 7As to maximize our compute cores. The HPC 7As have physical cores too, which is required for simulation software. Alongside this, using EFA for improved communication speeds across nodes, and FSX for Lustre for high access to S3 data. alongside some visualization nodes, so our simulation engineers can keep everything contained within their cluster when they're checking outputs. And then if we look at our machine learning architecture, we're using AWS batch, typically for multi-node parallel processing in EC2 mode for GPU access. We scale between 16 P5s for our larger runs or 8 P4Ds, so between 64 and 128 GPUs when we're doing training. And again, using FSX for Lustre for high-speed, low-latency data access, and EFA for fast inter-node communication through NVIDIA GPU Direct 2. So that is a look at our architectures. And it's worth noting that physics-informed machine learning is changing how people design, optimize, and manufacture. When a model is trained on a set of simulations, you can predict the results for simulations you haven't yet run, further exploring the design space to get that optimum output. And that gives you clearer physical designs more quickly at a much lower cost. The inference can take less than a second. So you're talking 20, 30 designs across half an hour at least. And physics-informed machine learning makes sense because physics and machine learning have a common shared goal, which is to accurately model the world. And that's what we're doing at PhysicsX. I'm going to pass back to Srinivas now to finish us off.
Excellent. Thank you, Jake and Harsha. So you've seen in the last half hour or so how customers like Merck and PhysicsX are combining HPC and AI for really accelerating their innovations. Coming back, this is where we started. So very quickly, I'm going to touch upon the third domain, which is also super interesting, where we are starting to see the convergence of HPC and AI, which is really around weather and climate. So what we have been doing here is, if you look at the landscape of how this particular domain is changing within the weather and climate modeling, this has been a classic HPC workload for almost 3 decades, where customers have been using traditional high-performance computing to run these weather models at scale. But in the last few years, there has been the emergence of these ML infusion across these physics-based weather models, whether it is Amazon's Prediff or Earthformer, ForecastNet from NVIDIA, GraphCast from Google, Pango Weather from Huawei, et cetera. All these different models, they're infusing AI and ML techniques into weather and climate prediction. For this particular work, we've actually collaborated with NVIDIA, and we have taken their Earth-2 platform for our weather and climate modeling. So Earth-2 is basically a full-stack platform that really covers traditional physics-based simulations, visualization, as well as infusing AI and ML models into these traditional physics-based simulations. It has a collection of different applications called Modulus, which is basically the repository that provides all the physics ML models for a variety of physics. Earth Studio, that's used mainly for our weather inference as well as training pipelines. And finally, Omniverse, which is mainly used for photorealistic rendering. So what we have done is, this is really the pipeline. We have in fact published a blog a few weeks ago that really talks about how you can actually optimize running Earth-2 on AWS, be able to do real-time weather prediction, and use the data, in fact, for downstream applications. For example, a practical application of using weather data beyond general weather prediction is for energy trading, right? So this blog basically talks about being able to use real-time weather predictions using AI/ML models and using all of the data for energy trading applications. And this is how you can see here. This is a quick snapshot of our medium range weather forecasting. On the top is actually the surface wind speed, on the U as well as in the V directions. And on the right-hand side, you're actually seeing the ensemble results. Oftentimes, you're not just running a single simulation. You're running hundreds of or even thousands of simulations, right? So on the right side, you're seeing an ensemble of all those results. So as you can see, in the last 45 minutes or so, we have really talked about our AWS HPC services. You've also seen how Merck and PhysicsX have been using some of these services and accelerating their innovation within their organizations. One of the key aspects of how customers are able to successfully run all these applications is a strong partner ecosystem. This is a very small snapshot of our partner ecosystem across our ISV partners, hardware partners, consulting, SI, and GSI partners. all of the innovations that you have seen in the last 45 minutes, as I said early on, AWS has been investing within the high-performance computing space for almost a decade now. And at the recent supercomputing conference 2 weeks ago, AWS has been voted as the best cloud HPC platform for 7th year in a row, recognizing all these innovations that we are doing on behalf of our customers. With that, I'd like to thank you all for your time and attention today, and if you can take a quick survey towards the end, that would be great. Thank you so much again.